Here's a video presentation where I develop a 3D model for a project using AutoCAD. In this model, the individual piece parts were made using something called Specification-Based Design rather than using conventional drafting methods. Conventional drafting methods would make each part manually within AutoCAD, where Specification-Based Design takes advantage of the VBA module that comes with AutoCAD. And through the VBA module, a user form is provided the designer. The designer puts in the geometric and material properties for the part, and then AutoCAD can compare that data with the existing database to find out if that part already exists. If that part doesn't exist, AutoCAD will make it once the data is submitted. Otherwise, AutoCAD will return the part name. So it makes for more efficient part management and data management for a project database or a part database. This example would also apply to Inventor. Inventor has a VBA module with it as well, so specification-based design can be used to make parts within Inventor rather than going through and manually producing each one or copying a part that's similar and then applying features to that part to make a new part, where the drafting department might have different characteristics between each of its drafters on how each of those features is done. Specification-based design keeps everything consistent and also maintains the data so it knows what the actual features are, what their sizes are, where they're located from the edge of a piece of sheet steel, for example. So when trying to find an existing part in a database, it's very quick and it's efficient for the design department. The other thing about specification-based design is in my comparison has been it actually advances a drafting department up into a design department. It provides data to other departments. So a drafting department will open up AutoCAD or Inventor, make the part, put it on paper, put dimensions on the part, and then close the drawing, close the program, and they're done. And the other departments have to work off paper sheets for the data they're going to use. So estimating, purchasing, fabrication. Fabrication has to transfer information off paper drawings onto sheet steel so they know where to weld the pieces, where specification-based design actually allows for parts to be etched a little bit easier so that you can get rid of free measuring in the production department. And then for purchasing and estimating, you have a single source model where all the data can be exported, and that data can then be manipulated through Excel to come up with material utilization and cost estimating. And so in this example, what I'm going to do is a timber framed garage. It's 30 feet along this wall and 24 feet across. So before I move into designing this project, I'm going to do just a quick example of how I approach 3D drafting in AutoCAD. So I'm going to build a couple of parts using the commands that I use for 3D drafting. I use UCS, 3D orbit, extrude, subtract, and hide. And that's pretty simple. A lot of people think 3D drafting needs to be complicated, but if you break it down into its components and understand what commands you really need to build a model, you can do some pretty amazing things with it. Things that are very useful from a production standpoint, which is my background. If you want to do more rendering and more presentation type models, you're going to need to go a little bit deeper than what I'm going to show here. But from a production standpoint, where you just have a good solid 3D model that can be checked for fit, quantities, things like that, that's all you really need are those 5 commands. So with that, I'll just move forward on to the next part. Okay, I'm going to start a new drawing. And the first thing I'm going to do is set UCS follow to 1. And then I'm going to zoom out. And what I'm going to do for an example is I'm going to make a 92 5/8 inch stud, and then I'm going to make 120 inch plates, and I'm going to make a simple stud wall. So I'm going to start off making the stud first. So it's going to be a polyline. I'm going to start it at 0, 0. I'm going to go over 92 5/8. It's a 2x4, so it's 3.5 inches wide. And so I've got that drawn as a polyline, and I'm going to extrude it, select it, and I'm going to go into the page 1.5 inches. And so it's made a 3D part. So if I UCS around the X 45 and UCS around the Y 45 and hide will get rid of any of the lines that are in the background. So now you can see the part. You're looking from this direction over here on the right. You can see the end of the stud. Here's the 1.5" side, and here's the 3.5" face. And so when I draw these parts, I draw them in profile. And the profile is with the thickness into the page by my definition. And so when I bring it into my component, when I'm building the components, it's important to know what axis I need to be rotated around when I bring those in. So the next thing with this stud is I'm going to subtract out a hole. I'm going to do a circle. Let's put it in the middle of the stud too. So I'll come down here 1.75, do diameter of 2.5. So I'm going to extrude that. And I'm just going to go a bigger number, like 10. And then I'm going to rotate it about the X 90 degrees. And I'm going to move this up like 2 inches, just so I know that it crosses the stud and it goes through. I'm going to rotate it back, and then I'm going to subtract. And when I subtract, I select the object I want to keep, and then I select the object I want to subtract. And so if I rotate around the X 30 degrees and do a hide, now it's a hole, and you don't see those lines extending above and below. Now it's a 3D object with a hole in it. So I put it back to its home UCS. I'm going to W block this out, and I'm going to call it ST1. Go ahead and replace it. And I'm going to select 0, 0. And there it is. And so now I'm going to make the plate. And I'm going to zoom out a little bit further. It'll be a 10-foot plate. And then I'm going to extrude it 3.5 inches, or 1.5. So if I do that around the X, hide, there you are. So the UCS is pretty, if you ever get lost, just type in UCS, it'll take you right back to the home position. And the thing I do mainly, if I type in X, it defaults to 90 degrees. If I do Y, it defaults to Y90. So typically what I do when I'm making parts is I'm just rotating about the X. And then if I want to see it, I'll rotate it around the Y if I want an isometric. I'm going to W block that out. I'm going to call it PL1. I want to overwrite the one that's in there. And there it is. So now what I'm going to do is I'll start a new drawing. And now I'm going to make the component. I'm going to make the stud wall itself. So when I open up my default AutoCAD drawing, I'm looking down on the building. So it's my plan view. So I want to bring the parts in so that their profile is in that view. So when I bring in the plates, I'm looking down on them. So I'm looking at them along their length and their width. So I'm already in the proper UCS view. So I'm going to say UCS follow to 1. I'm going to XREF and attach plate 1. I'm going to set it at 0, 0. And then I'm going to zoom out, and then I'm going to UCS about the X 90 degrees. So I'm going to build this wall around a 2-axis system. So I'm in the view where I'm looking down at the plan, and then I'm rotating the wall so I can see it in elevation. And the elevation view is the one where I want to place the stud. So that way I'm looking at the studs in their profile view. So I'm going to go in and I'm going to do an XREF, attach, and then I'm going to place the stud. And what I'm going to do is just place it like right here. I'm going to rotate it 90 degrees, and I'm going to move it so that it's down right here. Then I'm going to go back to my home UCS, and I'm going to rotate this stud. I'm not going to pick any objects. I'm just going to rotate it 90. And then I'm going to move it so that it's right here at this corner. I'm going to go back to the elevation, so I'm just going to rotate the X 90 degrees. It's placed properly. UCS icon, a lot of times I just shut that off so I can work in here. I'm going to go to 2-foot center. I'm going to array this. Rectangular array, I'm going to go, I'll just say it's 6. And I'm going to go 24. And then I'm going to move this over at 0.75. That's the layout. So now I want to put in the top plates. So the plates are 1.5 inches wide. The studs are 92 5/8. I just want to offset that, and then I'm going to copy it 1.5. And there's your wall. And so that's how I make the components. Okay, so I'm going to move forward here, and I'm going to do an example of a garage. It's a 24-foot wide by 30-foot long garage. with just a common 512 roof. In 3D modeling, I'm going to do it in a 3D model, and I'm going to start off showing you what the garage looks like, and then I'm going to model a couple of the parts standard, and then I'm going to do a specification-based design to do those same parts to show the differences in the data management capabilities. And then I'm going to do the entire model in a sped-up video that takes about 17 minutes to do. So what I'm hoping to do here, I know this video is going to be a little bit longer, but it covers a lot of topics. And basically what it is we're taking a lot of simple things. That's what 3D modeling is, just take a bunch of simple things and put them together to make one big complex looking thing. So if you just keep things simple, it's fun. If you make things too hard on yourself, then it just becomes frustrating. So first off, I'm going to open up the 2D version here. So we've got the 2D garage. And so there's a plan view here, and it's 288 inches wide outside to outside of sheathing, 360 inches long. It's got an overhead door here on the front, a man door on the front, 2 windows on each side, and a man door here in the rear. Here's the roof outline. That's the hidden lines of the walls, and then you have a 24-inch overhang, typical on all sides. The tail length is going to be 22.5 inches for the framed length of the rafters and hips, because there would be an 1.5 inch freeze board around here. So the horizontal run for the tail will be 22.5. So in elevation, here's the front, simple door, overhead door, man door on the back on the rear elevation, and then you have 2 windows on the sides that are symmetric. 512 pitch on the roof on all sides, and then I went through and I drew these up as more of a representative way but to represent how to do 3D drafting, this is a good representation. So instead of trying to do the entire model in one session, break it into components. And before Inventor, that's kind of how it works. You build parts, and then you make subassemblies and weldments, and then you take those subassemblies and weldments and you put those together to make the larger product. And so in AutoCAD, one of the things when I was talking to people about 3D is I would always tell them, hey, just break it into components, because if you try to build this building in one model, what happens is you get the front wall put in, but then all of a sudden you have this third axis you're always dealing with, and it ends up causing you issues when it comes to you're working on a 2D screen basically. So if you have that third dimension active when you're trying to actually model, it'll drive you crazy because things will get offset. It's hard to locate them. So do it all in basically a 2D format. So what I'm going to do is I'm going to build the front wall first, then you build the rear wall, and you do them in 3D, but they're on a 2D plane basically, and then you do the right and left walls, and then you do the roof joists because they're all in the same plane. Then I'll do the rafter framing, and even though each face is in a different plane, these are pretty easy to do because you can mirror and rotate things, and they keep their planes pretty well. So when you rotate about this face or this group of rafters over here about the center of this ridge, it'll make these rafters right here, and they're all in the same plane. It rotates the plane too and keeps everything. And then you do the roof sheathing. I'm going to do the roof sheathing this triangular face separately from this side face because they're on different planes. And then to do the 3D model, you just assemble all those different entities together. And so let's open up the 3D model. And so I'm going to hide it real quick here. And so you've got the roof framing. So if I highlight one of these, I hit the roof framing, you can see the whole thing is just a block. In a 3D model, a lot of times this looks like spaghetti to people who don't have a perspective on it. But you're looking at the rear left. So here's the man door and the 2 windows. This is the left wall. I'm going to turn on the sheathing. And if I hide it, it gives it a little bit better perspective. So here's the rear roof face. That's all its own block. Here's the side face. It's its own block. So that's everything. The wall here is its own thing. And they're just, I came into this drawing and I just took all those components and just put them together. So there's the 3D model. That's what it should look like when I'm done. I'll do one from the front right. And so there's the overhead door with the man door. Okay, so let's go make some parts. So I'm going to So let's close this out real quick. And since I'm doing the rafters and hips, I'll show you how to figure out the rafter lengths, how I came up with these dimensions. But here's the dimension. We're going to do 155.1875 for one of the common rafters. I'm going to do 211.174 for the hip. And then the studs are 104 and 5/8 because the wall height is 9 feet. Where is that? Right here. 104 and 5/8 inch studs for a 109 and an 1/8 inch wall that has one bottom plate and two top plates. And then the joists themselves are 288 inches wide. So I'm going to make this joist, I'm going to make a stud, I'm going to make the hip, and I'm going to make this common rafter. So to figure out the hip length and the rafter length, basically you just have to find the horizontal run from the face of the ridge to the edge of the wall. So it's 143 and a quarter, and you need that in feet. So 143 and a quarter in feet is 11.9375. So to figure that out, I've got a program that gives me roof factors. So if I just do a 512 roof, this will do mixes. It'll do combination roofs. So it'll do like a 612 and a 1012. Typically when I framed, we did combination roofs, which would be maybe like a 612 and a 1212 mix. So they're a lot more complex. There's a lot more factors, and the combinations are endless. So they finally came out with the Roofer's Bible, which I didn't have back when I was framing. So I just figured it all out. I had a Commodore 64 at the time and was able to come up with a program similar to this to give me the factors. So I'm going to export the factors to a README or to a notepad file so I have them. So let's figure out what the rafter is. So we know that the common factor is 13 inches per foot run, and the run is 11.9375. So if you take 11.9375, we'll do it in Lisp, 11.9375 times 13, 13, is 155 and 3/8. And then for the ridge, for the hip, it's got a hip factor of 17.69. So we're going to take that same thing, and it comes up with 211.174. So that's how I figured out those values. And so that's just based on the geometry of the roof. So let's go ahead and get off of that topic, and we'll start making some parts. I'm going to do the stud first. It's 104 and 5/8 long, and then it's a 2x4, so it's 1.5 inches thick by 3.5 inches wide. So I'll just do a polyline. I'll start at 0, 0, turn on ortho. And so there's the stud. I'm going to extrude it. I'm going to hit it here. And I usually go into the page, so I go negative 1.5, and then it doesn't have a taper, so it's just 0. I do UCSX. I'll do 45, UCSY, 45, hide. Then there's your stud. And so I do this. I'm going to W block it out. I'm going to put it into timber parts, and I'm going to call it ST1. And then I'm going to select 0, 0, all, and that's done. So then I'm going to do the joist, which is 288 inches long, and then it's got a 4-inch nub on each end. And so let's go ahead. I'll do that. I'm going to zoom out just a little bit further. We'll make that a polyline. Let's see, I'm going to do this just a regular line. This is a little bit harder. 288. I'm going to go up 4. And then I'm going to go back at 12, 5. I'm going to mirror that. And I'm going to offset this 11.25, which is a 2x12. It's 11.25. Fillet radius 0. We'll just, we'll just fillet this out, and then I'll make it a polyline. And so there we go. I'm typing a lot more than it. Usually I'd have these things shortcutted out a little bit, but for this example, it's not too bad. Here, so we'll W block that out. I'm going to call it joist 1. And so that's good. So then I'm going to do the rafter, or the hip next. So polyline, 0, 0. It was 211.174. And it's going to be a 2 by 8, so I'm going to offset this 7.25. I'm going to shut off the UCS icon just so it's not in my way here. And then the slope on the end of this is going to be a 517. So if you look back at this, hips, common roofs, the hip is divided by 17. So if the common roof is a 512, the hip is a 517. If it was an 812 rafter, it would be an 817. For combination roofs, that all goes out the window, but 17 is the magic denominator for hips on a common roof. So what I want to do is I want to come down 17 and over 5. So that gives me the pitch there at the end. And then I just want to copy that down, and that will, whoops, perhaps it thinks it's a polyline. Copy, and we'll just go to here. And so then I want to make the tail on that. 22.5 would be the rafter run. So I want to take 22.5 divided by 12 times the hip factor, which is 17.69. And it gives me 33.16. So I'm going to offset that 33.16. And I'll let you trust me on that one. I'm not going to waste any time on the video making this any longer. So that's the tail. And now I want to make the seat cut. And the seat cut's going to be 4.5 minus that 0.221, which is the hip drop. And the reason we need to drop the hip is so that the shoulders of the hip, because of its width, line up at the rafters. Otherwise, the hip would sit up about a 1/4 inch higher. And so when you brought your sheathing across, it would actually have an upward on it. It wouldn't be in plane with the rafters. So you have to drop it a little bit because of that, just because of the width of the dimensions of the lumber. So I'm going to draw a line that's perpendicular to this line. I'm going to move it up to here, and I'm going to, whoops, move it up to here, and I'm just going to make it so that the hip drop is 4.25. 0.221 is about a 1/4. So that's my seat cut. Then the tail itself extends down vertically 10 inches from the top of the wall, which is what this line represents. And that's just another trust me number, but that's typically what it would be based on how we used to frame. So I'll fillet that out to make the tail. Fillet. And I'll just go through and then we're going to p-edit this. I'm going to join it. Extrude. Negative 1.5 and 0. Okay, so this is what I have. So that's my hip. Now, what I want to do is I want to actually rotate that hip so that these ends are sitting vertical. And so right here, the hip back bevel is 16.39 degrees, which that's what this angle is right here. It's 5 divided by 17, and then arctan would give you that angle. So I'm just going to rotate it, negative 16.39. So that's how it would sit. So now this line's horizontal, which represents the top of the wall, and this line's vertical, which represents the face of the wall. And so what I need to do is I need to bevel the ends on that's why I've done that. So if I do a simple UCSX, I'm looking down on the part. I come in here and I do a polyline from the center, half the width, and then I'm going to mirror that. And then I'm going to mirror it about this end, about the length of the rafter. Then I'm going to extrude all of them, some huge number. It needs to be something deeper than the piece. So I just do negative 100. And then I come back, and I need this extrusion to cross the end, so I just drop it straight down. And then I drop this one down a little bit too. And then I come back, and now I'm going to subtract to get those ends to work. So I pick the object I'm going to keep, hit return, and then I select all the objects I'm going to subtract. And there we go. There you go. And so that's your hip, or that's the hip. I'm going to extend that out. And now I'm going to W block that, and I'm going to call it hip 1. 0, 0, all. So there we go. Now I'm going to do the rafter. So the rafter is 00155.625 or 1875. I'm going to offset it 5.5 for a 2x6. The end right here is going to be a 512, so I come down, I go over 5 and down 12. Fill that out. Copy. And then I'm going to offset this 22.5 for the tail. So basically the same as the hip, but a little bit easier because you're working with a 512. Four and a half seat cut. We'll fillet this with this. I'm going to offset this 10 and we'll just fabricate the tail here. The good thing about this one is it doesn't have any bevels on it, so I don't have to worry about doing that extra extrusion. So join all. I'm going to rotate this, which would be, for a 512 is basically 22.619 to get it in its vertical position. And then I want to move this, and I forgot to do that on the hip. I want to move that to 0, 0 so everything planes out at the same point. Rather than having this be my insertion point, I want it down here because that's where everything has common alignment. So I'm going to block this out, and I'll go back and fix the hip so it's different. Oops. I'm going to call it Rafter 1. 0, 0. And I'm going to open up the hip. Oops. And I'm going to move this point right here to 0, 0. And save that. That way, when everything comes into the model, you're working from the same plane. And so that's how you make the parts using just hand design. So in my database, here they are. I'll get rid of that back file. So I made those 4 parts. Okay, so now I'm going to make those same parts using specification-based design. And so I'm going to make the hip, the joist, the common rafter, and the stud. And I'm actually going to make the first jack rafter on each side of the common rafter on the hip ends. So it's the first rafter that frames into the hip, and so their lengths are 129 and 5/8. One has a left-hand bevel at the top, and the other one has a right-hand bevel. And so the specification-based design, when I do that, when it actually runs, it'll end up putting the parts in this AutoCAD timber parts database, which there's nothing in here right now. There's going to be an Excel file made, timber.xlsm, which is going to keep track of all the parts I've made. But since this is the initial running, it's going to have to make all those. So there's nothing in the folder right now. When I get done, there should be stuff in there. So to run the program, I have an icon up here called Make Timber, or else I can just hit MKT, and it'll call the VBA program. And so it comes up with a user form. I can make headers, hips, joists, plates, rafters, ridges, roof sheathing, studs, valleys, and wall sheathing. And if I wanted to add to that, I could. I could make collar ties and different types of bracing, which I'm not going to show in this example. For this, it has rafters, valleys, and hips, which are a little more complicated. They're about as complicated as any framing part you're going to need to make. So let's start off. I'll make the hip. And so when I hit hip, it knows what the different options are. So it knows it needs the roof pitch, the tail length, the seat cut, and the hip drop. And so I'm going to make it a 2x8. And it's going to have a length of 11.174. Its roof pitch is going to be 5, tail of 22.5, and a seat cut of 4.5, and the hip drop is 0.221, which is from this notepad file we ran earlier. So the hip drop's 0.221. And once all that's filled in, it automatically fills in the descriptions. I can't modify this at all. I'm locked out. Even though the cursor will go down here, I can't type anything in there. So the comments are filled out by all the fields over here, and the description is filled out by these 5 boxes right here: the part type, the width, length, thickness, and material. And so once it's got those filled in, this Add Part button comes on, and it just tells me that I can now add this data because it has enough data to make the hip. The part count is 0 right now because I haven't made any parts in this session yet. So if I hit Add Part, it tells me that the part I added is called Hip 1. and now submit data comes on, which means it has a part, and this session has one defined part, and so if I hit submit data, it'll go make it. I don't want to do that yet, so I'm going to just go make the joist, and now it tells me I've got one part count, or I've made one part so far in this session. And so I'm going to go 12, 288, whoops, let's see, joist, and it's got two, each end is nubbed, so it's 4.5 and 5. So we got that. I'll make the rafters. I'm going to make that a 2x6, and the common rafter is 155 and 3/16. This is going to be SPF. Roof pitch of 5, tail at 22.5, and the C cut is 4.5, and no bevel. And I've got it so I can just double click the user form down here, and it'll add the part once it's available, just so I don't have to keep coming up here and hitting the add button. I do that just for me because I get tired of chasing buttons around on the screen. So I'm going to make the first two jack rafters, and they're going to have 129 and 5/8 is their length. One's got a left-hand bevel, the other one's got a right. And so I've got those two made, and then I'm going to make the stud. 2x4, 104 and 5/8. I add that part, and so then I just hit submit data, and it's going to go through. The first thing it does is it checks to see if that database file is there, and since it isn't, it's going to make it. So it pops up with this Excel VBA project window because it made a macro-enabled workbook. So it made the hip. Now it's making the joist. It's making the rafter. And when you look down here on the rafters and hips, it says sub get overall length. Well, that's another macro in here that it runs just to get the overall length for hips, valleys, and rafters, because they're odd shaped. They're not, the length you input isn't the same as the length they actually are. So for material utilization, I've got a program that runs to find out what the overall length is. And then it has a column in the Excel database that tells it that, hey, here's the actual length of the member. So when I do material utilization, it knows what the overall length of the part is for those members. And so here it made all these parts, and it made this timber XLSM file. And so in there, it puts them in alphabetical order. It's got rafter 1, and it's got an overall, so it has all these, I'm going to shrink this down just a tick. Let's go down to 70. Let's go down to 85. I think I can fit it on there. Okay. So you got the part name, and then over here you have overall length. And I've got 181.534 is the overall length of the rafter, the common rafter. The input length was 155 and 3/16. The overall length is 181.534. And so when I go to AutoCAD, I'm going to open up that. I'm going to open up that rafter, and we'll just check and see if it is actually 181.534. So I'll just draw a line perpendicular to the rake. I'll move it up here. Then I'm going to offset it 181.534. And what it should do is it should be exactly in line with this tail. So if I extend that down, that's the actual length. So when I do material utilization, let's say I build the 3D model, I export the part names, and then I run them through some other Excel files or Excel macros, and it does a material utilization. It knows that it needs a 16-footer to do that rafter. And if it had like a 12-inch 2x6 that it needed for blocking, it would combine this part with that part and give the manufacturer or the guy out in the field, it would give him a list of parts that go on each length of lumber. So not only does it determine what lumber sizes you need for the actual job to order from the lumber yard, you also have material cut sheets that you give to guys out in the field so that they know exactly what parts come from what pieces. And it makes it more efficient, and you're not chasing material around, and they're not making their own decisions. And then everything ends up working out efficiently. So it works out for efficiency's sake, and it works out for production's sake because it's a lot quicker. Okay, so now I'm going to go ahead and I'm going to make the rest of the jack rafters using the same specification-based design. And now that it has a database, when I run the timber file, and I'll do it from the icon this time, what it's doing is it's populating the existing parts array. So what it does is it goes and opens up the timber XLS file. and there were 6 parts, so you saw it counted up to 6. And so there are 6 parts in the database. It populates an array, and so when I'm in here working in this session, if I try to duplicate an existing part, it lets me know. And so I'm going to make the rest of the jack rafters, and I'm going to assume I don't know any of them have been made yet. So I know that the first one's 129 5/8, 22 and a half, 4.5, and it's got a left-hand bevel. So when I do that, it tells me, hey, that part exists. It's Rafter 2. So then I go in and try to make the right side one, and it tells me it's Rafter 3. And so I say, okay, well, I'll make the next one, see if they're in there. So the next jack rafter will be 103.625. And I'm going to give it a left hand. And since it doesn't have that in its database anywhere, it'll allow me to add it. I hit right. It allows me to add that. It's Rafter 4 and 5 now. And if I go back and hit left, it knows that Rafter 4 has already been defined. So I'll just hit Submit Data. And it'll make both of those rafters then and add to the database file. Okay, and so I'm going to open up one of these rafters I just made. Open up that one. We'll do UCSX. So you look down, it's got a bevel on it here at the end. I'll open up HIP 1. And so really to do this by hand, it's methodical, but it takes some time. If you have it programmed in, it's a lot quicker. And the beauty of the specification-based design is, it's through an Excel VBA. What Autodesk products are really good at using Excel, so they're Microsoft Windows based, so you can really integrate the program itself with other utilities that come naturally with Windows. And so you don't even need AutoCAD to make these parts. You could go through and you could do the user form through Excel itself. It'll populate that database file. And then you can, when you get access to a computer with AutoCAD, you can actually go make those parts that it doesn't have in its database. I'm going to go in here, I'm going to delete all the parts I made. And all I have is this timber database. So I made the parts. I don't have AutoCAD. I had a laptop on an airplane somewhere where I didn't have a mouse or anything. I had to use a little keypad. Well, to do data management where you're just typing in numbers, you can do that. Just using Excel, if you're in a location that it's not conducive to either doing the drafting in that location or you don't have AutoCAD with you, you can still be productive. So let's say I did that. I made these parts through Excel, so I have this database file. I get to the office, I get on a computer that has AutoCAD. And so now I'm going to come up here and I'm going to use this timber from database program. Or else I can just type in TFD. And it asks me if I want to update the overall length. I don't need to because it already figured it out. Or I'm going to say yes, just because if I did it through Excel, it wouldn't know what that is yet because it needs to have the AutoCAD drawing in order to do it. It figures it from the AutoCAD model. So I'll say yes. And then it's going to go through. Right now it's populating the data from the Excel database. It found out which parts have not been made yet. And then it just goes through and it makes them. So it went ahead and made those parts. Okay, now what I'm going to do is actually build the entire 3D garage example from scratch. So I'm going to go through and make all the parts. There's 71 parts in this model. So I'm going to generate all the parts using specification-based design. And then once the parts are made, I'm going to build the components, and then I'm going to take those components and put them together to make the 3D model. So I'm going to go ahead and start this example. And this is a video of my screen when I actually did the process. And for me to do the process, it took just over an hour to do the entire design. And so then I took the video and I sped it up so that the video itself only takes about 17 minutes to run. Otherwise, this video in total would be, it'd probably be close to 2 hours or over 2 hours long. So by compressing this, I can show the process, but yet not just be overbearing with the time frame. So right now I'm inputting the data for all the parts, and at this point, this timber parts file or folder would be empty. There wouldn't be any parts in here, and there wouldn't be this database file. So right now I'm inputting, and then when it makes the parts, it populated this folder. And it made this timber XLSM file, since it was the initial part generation thing. It made that file, and it put all the data in this sheet. So, like I said earlier, let's say I came back and I was going to do another project. Any of the parts I'd made previously would tell me they were already made, so I don't end up duplicating the same tasks. And here it's just making parts, but typically in a real project you would have drawings of those parts, so you'd have them dimensioned and maybe even PDFs. And if you're duplicating that effort, it can be pretty substantial. And then if you're dealing with steel and lasers and you've got part numbers that are out in your laser databases, if you're regurgitating information, you have the same parts under different part names, and it's just a lot of duplicated work. So having something as simple as this to tell you whether or not you've built a part before saves quite a bit of time down the line and keeps your database efficient, so you don't have a lot of duplicate parts throughout. One of the good things about this too, one advantage is where I used to work, they had an ergonomics team, and so what I'm doing when you use programming like this is you give AutoCAD some data. You're basically given AutoCAD direction rather than having to punch in every single command and get one response back. By giving it an envelope of information with some programming to help it understand what that information is, you give it information and then it'll run 2 or 3 or 4 or even half an hour without you having to do anything. Well, it just processes the information for you. And the advantage to that would be, one would be ergonomic. Where I used to work, they wanted us to break our posture every hour. People, when they work at computers, have a tendency that during that time they'll start moving their heads forward and they won't blink as much. So it causes some posture issues, some neck tightness. You can have vision problems, all kinds of different things can happen. So ergonomically, if you're doing something like this, when you start running this program, you can break away from your computer for that moment. You can get up and stretch or go use the restroom or return a phone call or coordinate something with somebody while your computer generates the data. Basically, your computer can stay busy while you go do other things. So you're basically managing a really powerful employee. It's not very bright, but it follows every instruction you tell it to do. So the computer, if you give it a bunch of tasks, you delegate information to it, and then you let it decipher that information for you through programming, you can save yourself quite a bit of time, and it's got a benefit to not only efficiency as far as getting projects done quicker, but it's just easier on the person working at the workstation as well. So right now what I'm doing is I'm making the front wall. And I said earlier that when you do 3D drafting, to make it simple, so I break things into components. So I'm going to do the front wall, the rear wall, and the side walls, and do everything component-wise. So basically what I'm doing is I'm working around 2 axes, where if I tried to build this building just in one drawing and bring all the components in one drawing and tried to place them in a 3D setting, it's difficult. I've always had difficulty doing it because it's that third axis of AutoCAD that gets you into trouble. When you're working on the screen like this, you're working in a 2D graphical environment. So it's that third axis that always gets you in trouble. It's the one that goes in and out of the screen, basically. So what I do is the AutoCAD standard, when I open up the template drawing, I'm basically looking down on the building. So for the walls, I'm looking down at the plates, and I'm looking at the studs in section. So what I do when I place my parts is I always place them in profile. So when I place them, I'm looking at their width and their length, and then their thickness is into the screen. So when I place the plates, I'm looking down on the building, so I'm seeing those in profile. I get those placed, and then I rotate it 90 degrees around the x-axis, and then I set the plate elevation in that. So I set it in the one plane, and then I turn it 90 degrees and set the location in the
other plane. So for like the studs and the headers and the sheeting, I do it in this with the X rotated 90 degrees, so I'm seeing them in profile. I place them in the profile view, and then I rotate it 90 degrees, and then place them like here the sheeting had to be moved to the other side of the wall, and then I place them there and everything lines up. If I try to do it in a 3D environment, what happens is I'll place them in two of the planes, and then when I go look at the third plane, it will have moved. And then I'll place it in the, I'll correct it in the third plane, and then I'll go back to one of the other planes, and by moving it in that third plane, it moved it out of alignment in one of the other two. And it's because of the snaps in AutoCAD. You know, you might pick the top of a member, and it's actually picking the bottom, and so it'll move it vertically up and down in that third axis. So doing it in a two-axis, just breaking components down so you can build them in a two-axis system is the way I would always suggest somebody do it, because it's just a lot quicker and a lot simpler. So now it's doing the rear wall, and it's got the stud set and the bottom plate set. Just putting in the headers, moving the blocks down in this plane, and then it's aligning the header in the wall plate, so that's done. So now it's putting in the top plates. So there'll be a little bit of dead time during this video. I'll think of things to say as we go along here, but I don't need to over-commentate it. I should have thought of some jokes or something, but the only one I can think of offhand is why can't a bicycle stand on its own? Because it's too tired. I don't know if that counts as a joke or not, but we'll just have to settle for that at the moment. So it's doing the rear wall, putting in the sheathing. I guess another example I'll bring up as far as efficiency goes is, you know, where I used to work, we used Inventor. Inventor is a great program. I mean, what I've told people, I've told people that AutoCAD, you know, they talk about the latest version of AutoCAD, and I've mentioned to people that AutoCAD 12 back in the early 90s had everything anybody needed as far as AutoCAD goes. There hasn't been a huge amount of improvement in AutoCAD itself from a production standpoint, either in architectural drafting or structural drafting or production drafting like this 3D modeling. It was all there basically in AutoCAD 12. And then AutoCAD 14 came out, and its change was that it used Windows 95. So it allowed for multitasking, because you could have AutoCAD open with your email and your word processing programs and stuff, because you were working in a Windows operating system. So what I've said in the past to people is that AutoCAD's versions are based on operating system improvements. Things went from 32-bit to 64-bit, and that's basically the steps AutoCAD's taken. There have been some improvements as far as like AutoCAD 2000 changed the plotting so that you could send just your line weights to somebody and they weren't integrated with your plotter. Before that, you had line weights were assigned to a plotter driver, and so I might have several clients I worked for, so we'd have one plotter, but I would have 5 different plotter setups depending on the line weights. Well, then when AutoCAD 2000 came out, you could just pick the plotter, one plotter name, and then you would just go pick the CTB file that you wanted, which was the line weight definition. So it was more streamlined there. AutoCAD 2006 came out with dynamic blocks, which are kind of a precursor to Inventor and what it does. But the engine's always been there. So whether or not you've used the latest version of AutoCAD or whether you've used one even like AutoCAD 14, I could do almost everything I do today with AutoCAD 14 and be as fast or faster than anybody I'm around. I utilize the program better than most people do, I think, because I use the program from a production sense. So all the bells and whistles and different shadings, and the icon looks different with the updates. The engine's still the same, and the value of that engine has been the same for well over 20 years now. So I was lucky enough to work for a company that I was able to see the utilization of AutoCAD early on, and then ever since then, everywhere I've been able to teach people things from things that I learned 20 years ago that improves their processes. So right now it's doing the joist. And I guess one other thing with efficiency thing, I think I was starting to get there before I got sidetracked with my AutoCAD discussion, was where I used to work, they did PDFs for every part they made. And so we would do jobs, and we would typically have maybe anywhere from 100 to 150 parts, new parts. So that would take anywhere from an hour to a little over an hour and a half to make those PDFs. When I first got there, the way they did it was you would open up each part, print it to PDF, and you'd have to, give it a name and click the dialog box, and the computer would sit there and make the PDF, and then it would be done, and then you would close the drawing and you go to the next one. And that process took basically, I would say a little, maybe 30 seconds to 40 seconds per drawing to do. Because I know we had one job, and I ended up writing a program so that I could do the PDFs automatically. And so there's something called Inventor Apprentice. It uses Excel. And so if you use Excel, it'll speak to Inventor, and it'll change things like iProperties, and you can print a PDF through Inventor Apprentice. And that's where I initially wrote the program through. And it would allow me to print the drawings off. They had one job that was 1,200 new parts, and they had assigned it. It was so big that they had determined that they were going to give it to 3 different people. Each person was going to have 400 parts to do, and they would take each person 5 hours. So it was 3 people, 15 hours total. And right now what this is doing is it's making the roof. I'll kind of move on. I'll talk about this real quick. So what I'm doing is I'm setting the hips. And this is important with roofs since I'm working in different planes here. I have my common work point for my rafters and my ridges is this seat cut down here at the bottom. So when I put the ridge in first, and then I drew a vertical line down the distance to the top of the wall, and then I drew a horizontal line across to set it. And so that's what I'm doing right here is I'm resetting all the hips back. That horizontal line right there represented the top of the wall. So now the hips are in. I'm going to shut those off and put in the common rafter on the end of the ridge, set it, and then what I'm doing right now is I'm putting in the jack rafters for the one side, and the insertion point is right here at that point. So this represents the horizontal line where the rafter would sit on top of the wall, and once those are in, I just go in and I pick the bevels and I just offset them a factor of 2 feet to lay that out. So I did the one side, and now I'm doing the other side of jack rafters where the bevel goes the other direction. And the insertion point, like I said, is right here. So that horizontal line represents the top of the wall, and this vertical line represents the outside face of the wall. Outside face of the wall sheathing. So I just make, that benchmark is always the same for all the roof members, regardless of their length. That's where they all work from. And so now I'm just offsetting these parts the other direction, so that they're on a 2-foot layout. Now I'm selecting the rafters here, and I'm going to copy rotate to make this side. Then I'm going to come in and copy rotate this group up here to make this side down here. This thing's moving so fast, I think it just looks like I'm arm waving. So, and so then I mirrored it around. I just copy rotated it around the ridge, and then I put in the rest of the common rafters, and then I turned on the hips, and everything was done. So it did the roof framing. And now it's doing the roof sheathing. And this is on the ends, so it'll be a triangular shape. And the way this is modeled is I'm looking directly at it, so I'm perpendicular to the sheathing. So when I put this into the building, I'm going to rotate the building 22.619 degrees about the x-axis. And so one of the faces of the roof is directly perpendicular to me, and then I'll place that sheathing on top, so it'll sit perfectly on top of it. The 22.619 is the angle of a 512 roof. And so I place the one end, and then I turn the building and I mirror it to the other side, and then I do the side sheathing the same way. I just rotate it about the x-axis, that 22.619, and then I put this down. So anyway, getting back to the Inventor thing with the PDFs, this is an example of some efficiencies that are available and are absolutely unbelievably huge what you can do with some of the programming here. So they had a job, it was 1,200 drawings, and they had determined, doing it their way, they were going to use 3 people, 5 hours each. Each person was going to be assigned 400 drawings. We used my program we had to do it within Inventor because when I used AutoCAD Apprentice when I first wrote the program, it didn't update the IDWs unless it opened up Inventor. So I needed to run that program through Inventor so it would open up the IDW, it would update the IDW, and then it would print the PDF. But all that was automated. But it took it 40 minutes rather than 5. So it took 40 minutes to print 1,200 PDFs. And it took one person that ran a command at the beginning to run the program, and then he just watched it and monitored it for 40 minutes. And so it freed up 2 people for 10 hours, and that one person that did the PDFs could multitask while it was running, and it saved him 4 hours and 20 minutes of time. And it also saved them from having to sit at a desk and just type in every single command, rename the sheets. It's just a tedious effort for practically a day's worth of work. And it allows all that time to be freed up to do other things. Now in this view you can see that the main joists are upside down. I got the main joists upside down. You can see they're flipped. So once I get the sheathing and everything put on, I'm going to go into that joist program and I'll end up mirroring those really quick. So right here I'm going to put in the sheathing. So I just rotated the building 22.619. This face up here is perpendicular to me. I'm going to place this sheathing right on top of that. So basically this is, and then I'm going to rotate it, I already mirrored it, so I'm rotating it so that the side is 22 points, so it's right perpendicular to me on this side. So really what I'm doing here is something that AutoCAD had available, years ago, and it's not quite as powerful as Inventor, but it's the foundation that Inventor was built from. And I've applied and there I just flip the joist over and then I just re-update the drawing here so then it's right. So, let's see, I think the building's about done. So that's it. So that's the 3D model. So from here I'm going to move forward and we'll start looking at doing a bill of material and processing the data for the job. Okay, so now I'm going to export a bill of material from this model now that it's built. And what I'm going to do is it's going to look at the blocks in this model and it's going to extract them out into an array, and then it's going to open up the Timber database and compare those part names or block names to the Timber database, and any parts that coincide it's going to export the data into an Excel file. And that Excel file is going to go into this folder. It's called BOM. It's under the AutoCAD BOM. So underneath here I've got my project and then I've got a bill of material. So if I was working in an office, that bill of material folder is where all the project's bill of materials would go, and then that's where you would process from. So I'm going to go ahead and export it. And when it exports, it's going to separate the roof sheathing, the wall sheathing, and the lumber from each other. And then once it's exported to Excel, I'm going to go ahead and I'm going to process the bill of material and do cost estimating and cut efficiency on the lumber only. I could do it on the roof sheathing and the wall sheathing, but the programming is quite a bit more complicated on that, and I don't have that. I don't have those programs with me here. But I was able to write the one up for the lumber. It's a little bit quicker. It's just linear. With the sheathing, it's more like nesting parts on sheet steel, so the algorithm's a little bit longer. So for efficiency's sake, I'm just going to do it on the lumber itself, just as an example. So to run the bill of material, I can click this icon. I made an icon up here, export BOM, or else I can just type in BOM at the command line. I'll just click the icon. And so what it's doing is it's getting ready. I found 71 unique parts. And so it's opened up the Timber database. And now it's coordinating that data. And once it gets done doing that, so what it's doing is it's searching through the database, and let's say stud 1 is ST1. It's in this model, so it looks in the Timber database. It finds ST1 and extracts the data assigned to that part number. Once it gets that array filled, then it goes and it makes a bill of material Excel file, which it'll do here in a second. It'll show up here in this folder. So there it is. It made an XLSM file called 3D Garage Blocks, which matches the project name up here. And now it's done. And so it's been exported. So the raw data has been sent out. And so what it has is it has the material properties, the part name, the thickness, width, and material for each part. And then it has quantities. So this is basically raw data. I'm going to stretch this out just a little bit. So there's the wall sheathing, the roof sheathing, and the wall sheathing. They're separated out because they've got different parameters. So when I'm doing material utilization, these long points are unique to the roof sheathing, basically. And so you could have a 72-inch long point and a 48-inch long point, and they both fit on the same sheet. And so the algorithm that it uses on this worksheet would be different than what it uses on the lumber worksheet. So they're separated out to deal with those algorithmic differences, I guess, to put it, I guess, in a fancy form. But so anyway, so I got this done. And so I'm going to go and I'm going to process the bill of material. So I'm going to close this file. And then I'm going to, I'll just expand this out. And in here I've got a file called process bill of material. So I'm going to hit it. It's going to come up with a user form. And so it's going to list all the files that are in that bill of material folder. And since there's only one in there, that's the only one listed. So I click it and the submit button comes on. Because it has a number for overage and it has a number for sales tax. I'm going to give it a 10% overage and I'm going to give it a 7% sales tax to calculate. Typically, the overage would be anywhere, especially with lumber, would be anywhere from 15% to 20%, depending on what I'm doing. The old way. The way this works is I've already got the material utilization figured out. So the material waste is already figured out through the cut sheets. So I can do 10% on lumber because it protects me a little bit in case there's a mistake made out in the field and we have to recut a piece or something. And then if you have bad, let's say you have 70 studs come out and you need 60 of them. And you've got 5 of them have a really bad crown or have a knot kicked out of them or something happened, you can just kick those to the side and not use them and send them back to the lumber yard. And so I've got a 10% overage figured in. So I hit submit. So it opens up the price. There's a price list database, which I'll show you here in a minute. It's got all the different materials that from the lumber yard and what their prices are, their current prices. Takes this bill of material and gets the price for each member, and then it goes through and does an efficiency based on price first. First, if all the parts fit on a piece, it looks at it, and then it looks at what the most efficient cost estimate is for laying out the parts on those pieces. So the original had these 3 sheets, and now after it's processed, it's got a cost sheet and it's got a cut sheet, and it's done it on the lumber. So I've got an actual material required and a material estimate with 10% waste. And so when I do the bid to the customer, the way I used to do it is I had fixed labor costs and I had material cost as a maximum. And what it said was, I give them a bid and it was not to exceed. And so the labor cost will stay fixed, and the not to exceed means that the customer won't pay more than $21.56.57 for the material. I expect to pay $17.56.67. So that's how I would work it. I would just come in, and this is the number that the customer would see on their estimate, and this is the number that I was hoping that it would be. But if I had any mistakes or anything like that, I had some wiggle room. So that's the pricing. So I've got these cut sheets, and these are in order of length. I'm going to take this, I'm going to open up the timber database. Okay, so the timber database is open, and so when I start off here, I've got 4 PL20s, and I'm going to cut them out of 2x4 by 192s. And so I come down here, they're 191.5. And so the guy out in the field is going to take 4 2x4 by 16s, and he's going to cut these 4 pieces. Then he's going to go get the other 2x4 by 192s, and he's going to cut 1 PL19 and 1 PL2. So a PL19 is 180, and a PL2 is 10 7/8. So this is exactly what you should cut out in the field, and it gives the guy out in the field, in length order. So go cut all the 2x4s, and you just start from the top, and you just work right down the list, cutting all these parts. And then when they're all cut and stacked up and staged, you go down the 4x6s, and you cut your headers, you cut your LVLs, you cut your southern yellow pine, and you know exactly what you're cutting from what piece. So you don't end up cutting something from a big piece of lumber and then run across something that needed that big piece that you forgot to cut, and all of a sudden you don't have the material on site that you need. I've run into that before, and this right here solves that problem. And it really gets cost controlled too. It's just a really good system. So that's that. And that's it. That's the model. I guess that's the example. All right, so that's a fairly simple 3D model that does more than just draft up parts and make prints with dimensions on them. This actually takes data, and you can do the design faster. And then when you're done with the design, you've got a lot more usable data that other departments can use rather than just taking paper prints and then providing their own material takeoffs. So estimating can use this model to get a good idea of what the parts are going to be without having to do their own legwork on it. Procurement can order, knowing what the order is going to be without doing their own takeoffs. Fabrication has a better understanding of how the parts that are ordered, how the raw materials need to be cut up or fabricated so that the material utilization is more controlled. And so it's got a lot of benefits. And since the design's faster as well, if you end up having a change or something happens on a project that you have to go back and modify it, the design's fast enough and the numbers can be generated quickly enough that, you know, changes aren't as big a deal. You can respond quicker. So hopefully that provides some understanding. Thanks.